in the cell proliferation, like cyclin D3, cyclin D1, BRAF, IGF-1, etc. So this caspase, BCL2, this is involved in apoptosis. So what you can notice is that when 43 sigma is downregulated, so the color is green. When the color is green, meaning that it's a downregulation, you see that it is accompanied by the downregulation of caspase, meaning that the cells will have less caspase for apoptosis, and the increase in the BCL2, which is a very strong anti-apoptosis protein, or CAP, or FOXO1, NAP, etc., BCL2L1. So suggesting that when 43 sigma is downregulated, then apoptosis of cancer tumor cells will be reduced. On the other hand, MMP 9, 3, 7, etc. increase. These are the enzyme involved in ECM degradation that will help the cancer cells to penetrate into the nearby tissue and metastasize to distant organs. So when sigma is lost, you see an increase in the cell metastasis. And similarly, tumor angiogenesis also increase when sigma is lost. And the cell growth will increase as well. And the inflammation also upregulated. And inflammation is one of the driving cause of cancer. And on the other hand, the DNA repairability of the cells is reduced, meaning that the cells can have more mutation. And my PhD thesis focused on the cell metabolism, and we discovered that 43 sigma, when this is lost, the cancer cells will significantly upregulate multiple pathways involved in energy production and also cancer metabolism. For example, these genes involved in the glycolysis, and this is lipid metabolism, and this is gluconolysis as well. So, and we use this figure for our high throughput screening, and also for our paper. And you can see, you can do a similar search, like you can study the impact of the gene loss or gene upregulation on the genetic change in the cancer cells as well. Now the figure we did is to study how obesity and diabetes can affect the patients. This is too complicated. So this is again, this is 10 cancer hallmark. This is the perimeter over here, and in the center, this is the receptor. This is the receptor and transcription factor, involved in the signaling of this cancer hallmark. So you can see this very tight connection between the cancer hallmark and this receptor. And what we found is that you see the color, we have the red color increase. In this case, we compare the obese breast cancer patients versus normal weight breast cancer patients. And we found that when patients become obese, then they have a significant increase in the signaling of multiple important transcription factor in cytokine. For example, like estrogen receptor, antibody receptor, IGF, which is insulin growth glycogen factor receptor, CD40, etc. And all of these receptors will transfer the signal to the other downstream genes. For example, here the BCL2, caspase 7, SMART3, etc. And SNEL, which is for EMT, epithelial mesenchymal transition, or Wnt signaling, notch signaling, SERPIN1. So you can see in KRAS as well. So the take-home message of this figure is that when patients become obese, all of the oncogenic signaling network that drive tumorigenesis will be upregulated. So obesity have a very negative impact on the patient's survival. So using IPA, we can know how obesity can affect tumorigenesis. So you can do the same thing for your study. For example, you can treat the cell with the drug A and compare the control and see what kind of change will take place. And IPA can help you do that. And this is, and you can use this as a figure in your favor. Okay.
So how to see the one relationship between one kind of gene to another one?
Say again, please.
How to see only one gene to another one?
How to see one gene to another one?
Yes, I mean one the connection of only one.
Okay.
So the question is how to see the connection from one gene to another gene, right? So this is the click here, for example, from E2F to MYC, for example. Okay. Should we click on it?
No.
If you want to display it separately, right?
No, I mean one kind, for example, E2F for,
Okay.
and another I want to see on.
So all of the other
Yes.
genes? Oh, okay. So in this case, we already used the tool Path Explorer. So it's already connect all of the potential connection already take place here already. For example, yeah, Path Explorer connect there pretty much the same. For example, ETF4 can affect 1, 2, 3, 4, 5. Actually, a lot of downstream packaging. So is that your question? You
Yes.
click here, you're gonna see this affect all of the genes right here. So all of the possible connection already displayed here already. There's no more connection.
Yes.
Okay. This everything already displayed here already. IPA can also allow you to do a core analysis. For example, you would like to know what kind of change, what is the gene responsible for the disease, etc. So in this case, you're going to use core analysis or tox analysis. If you would like to identify the biomarker, then this is the right option. In case some of us do a cancer metabolism study, then metabolomic analysis is the right option, and microRNA as well. Okay, I know this is pretty complicated, but if you have any question, please email me, and I will be happy to work with you. It's going to be, if you want to know about all of these functions, it takes about a couple of days to know about all of this. It's very complicated software. So what I just showed you is the most frequently used tool. For example, like designing a pathway and collect all the information, population contact. Okay. So I'm sorry that today we have to just watch this demonstration. I hope that when you go home, you can try it on your own because internet at home may be fast. So I think I will stop here today. And if you have any question, and if we have more time in the future, I would like to demonstrate you how to do for analysis and analysis as well, but not required to have the raw data. So for example, any of you would like to send me the raw data for demonstration or for analysis, I will be happy to help you with that as well. Alright, so thank you so much.